Good day to everyone. My name is Javier Suarez. I am currently a PhD student in Constructor University in Germany. My advisor is Professor Angelo Pio Rossi, and I am here to present you a part of my work in the geomorphological mapping of the Valentine domes on the Moon. So the Valentine domes are a set of intrusive domes that are located in the Serenitatis Basin on the Moon. And I want to give you a little introduction of why I decided to work in this location. So as you might know, right now we are in a kind of renewed space exploration stage. We have several agencies around the world trying to go back to the moon. And in this case, we have the idea to stay there. If we really want to do this, there is something that needs to be solved, and it's the necessity of resources. Of course, there has been a lot of advances in the identification of water and other volatiles, but the mineral resources are also important and interesting. And it's in this topic that the intrusive igneous activity and their derivative processes can be interesting to study. So for this reason, I decided to do a geological characterization of this location and an assessment of their potential as reservoirs. So here we have a map of the moon. We can see the near side. So we have all the different Mars, and we can see that the Valentine domes are located a little in the northern hemisphere. We also have like a close-up to the Valentine domes. As you can notice, it's not really easy to see them. And this is something that is common to intrusive domes in the moon. And further ahead, we will see why. So to understand the importance and also the rarity of the intrusive domes in the moon, we have to see something about this geological evolution. So when the moon originally formed, it was able to crystallize, to cool down in a relatively calm way. What this ended up doing was that the moon has a really differentiated crust and mantle that has really different densities. So we have a crust that is anorthositic and has a low density, and a mantle with a higher density and really ultramafic. What happens when an intrusive body tries to go out from the mantle? It will get stagnated and trapped in the lower crust because of the density. The only way in which an intrusive body can go into the surface is by two processes. One process is the impact of a really large meteorite that will be able to excavate all the way until the lower crust and even the mantle, and generate debris of this intrusive all over the highlands and the crust of the moon. And the other possibility is by the activity of secondary processes like the lava floods after a big impact that could eventually create things like dikes, laccolith, and these secondary magmatic structures that intrude the moon. So this is a little sketch of the distribution of these potential intrusive rocks. So as I was saying in the last slide, we can have some ejecta from really big impacts, and this ejecta will be probably mixed with the highlands, so with the highlands material, that make it a little difficult to identify. And the other option is, of course, the intrusion of lava floods from the mantle that can eventually form dikes, and for example, in this case, an intrusive laccolith. As you can see, all of these intrusive secondary activity can be embedded into the lunar Mars, so they might be common in this kind of situation. And this is, of course, the case for the Valentine domes. So the Valentine domes, they are located in the west margin of the Serenitatis Basin. It is actually really close to the rim of the basin, which is something important about the geological setting that we have in general. The Valentine domes were initially studied or identified by Lena et al. In 2006, and they were able to identify two main bodies. Valentine 1, that is kind of the principal body. It has 70 kilometers wide, so it's really large. And we have the smaller Valentine 2 that is located to the north. There is also a large fault that is crossing the east side of the Valentine wine dome. So it is interesting because there is a possibility that is a there is a way to for the lacolith body that is inside to reach the surface. As I was telling before, you can see that these domes are really wide and they have really gentle slopes. And this is a common characteristic of intrusive domes. Why? Because of course these are pockets of lava that are getting caught inside the subsurface, and they have difficulties to reach the surface. So usually we will have these extended morphologies that are characteristic from them. As for the data that we use, we focus it in optical and spectral data. For the optical part, we have data from the wide-angle camera and the narrow-angle camera. These are both located inside the Lunar Reconnaissance Orbiter. The first one allows a more general approach with usually 50 meter per pixels in resolution. And the narrow-angle camera can have resolutions up to 1 meter per pixel. So it's really good to do a small geomorphological interpretation. The second set of data, we have the spectral features. We have the general ultraviolet visible camera UVs inside Clementine that has really interesting spectral ratios. And we also use the Moon Mineralogy Mapper, MCube. That is a hyperspectral sensor that allows a more detailed mineral recognition. We also have another type of data. So we have the laser altimeter, that is a product that can generate a DEM, so a digital elevation model. And we also use the Grail data to have a kind of a view of what is happening inside the surface. We can proceed with the results of our investigation. To start, we have the geomorphological dimension of this study. Here we have the local geomorphological map. This was really an interesting exercise because we were able to identify really interesting things. To start, and most importantly, we have the identification of a third intrusive dome. This was really a surprise because we were not expecting to find something like this, but this dome is actually even more shallower than the other ones, so it's really difficult to identify them in low resolution data. This is really interesting because what it's telling us is that probably the intrusive activity in this location is bigger than we even expected before. This dome is actually a little larger than the main one, but it doesn't have a lot of other interesting properties that the main dome show. And with this, I am referring to the existence of several mouths, small hills, that are located inside the main dome. This is something really interesting because there is two options for the existence of these hills inside this location. One possibility is that they are remnants of the basement, so basically ejecta from the original impact that formed the Serenitatis Basin. So basically the same material that we have in the rim of the big basin. Or the other possibility is that they are actually secondary igneous activity, which will be more interesting. Here we have a profile of the two structures, so the main dome and the newly discovered dome. We can see that the topography of them is actually kind of similar. You can see the shape, and we can also see that they are more or less connected. And this is really interesting because, again, it is telling us that there is a relationship between these things in the subsurface. We can also see a profile of this structure and how they are connected. In order to solve the question about the origin of these small structures inside the main dome, we had to use the NAC data, that is the one of higher resolution, and we found really interesting things. So to start, these features are all really round. They have circular shapes. They are also related to secondary features like structural patterns that cross the main dome. You can see this large fault that is crossing northwest. And they also have a higher albedo than the mar around them. So all of these things points to an interesting relationship, because if these were actually remnants or debris from the impact, original impact event, it would be a big coincidence that they are all located inside the dome and focused in there. So this is not so likely. Also, we were able to differentiate from actual debris that they don't share this kind of round shape. They are not related with the main structures. And we can have like a difference between the two things. So we can see in blue the things that will be debris, and we can see in pink the actual secondary domes. So this is also another interesting feature that tells us that the system is really, it was really complex and probably reached the surface in several locations. We can see here in the Bouguer anomaly that there is an interesting donut anomaly below the domes. This can be the result of a buried crater, for example, of a volcanic anomaly or concentration below. So this can be also related to the existence of the intrusive domes, and this is something that we are evaluating. And finally, we have the spectral information. We use entry cubes to generate spectral indexes. For example, we have to the left the Clem-like index that is interesting to see the maturity of the rocks. So in the places that we have a more reddish color, we are seeing probably soils with more maturity, which means that they have been exposed more to the solar rays and they are older. In this case, we can see that this is a trend for the highlands and also for the blocks that are south of the main dome, which will support the idea that these are actually part of the debris of the basement, while the other smaller features inside the dome are actually part of the secondary activity. We also have the band deep number 1. This is an example of a band that allows to see the difference between the main mineralogy of the location. So with places with a higher absorption, so darker colors, we can see probably the location of olivines, pyroxenes, and clinopyroxenes. We also have these two indexes, the RGB one that allow also to see the maturity. So the darker locations have higher maturity, and the impact craters that you can see are more brighter, represent lower maturity because the soil, well, is fresher than the other one. And we also have the RGB2 that is interesting because it can show difference in compositions of the surface. So we can see that this one highlights really well the location of the secondary domes, as well as the material of the rim. So we can be sure that these things inside the domes are newly formatted structures that are independent from the previous geology of the zone. Finally, we can conclude that the Valentine dome system is more complex and bigger than we previously thought because of the existence of this tear dome, and also that the interesting connection between all these secondary domes, the intricate fault system in the location, and the accumulation of material inside the main dome, there is an interesting probability that the fluids and the minerals that accompanied this intrusion were able to reach the surface. So this is really important because if we're trying to look for potential mineral resources, these outcrops and these interactions might be really interesting and makes the Valentine domes a really interesting place to visit. So thank you very much for your attention. These are the references from this work, and if you have any questions, please let me know.